Hi, welcome to our presentation of our undergraduate classical mechanics project. We did a take on the classic phrase, when one door is closed, another one opens, and ours is when one door is closing, open another. Imagine you're walking behind someone at some speed v, and you both approach a set of double doors. As the person in front of you goes through the first door, you start to wonder that, well, because this door is swinging back towards me, would it be better if I went through the door that's closed or the door that's open? And the first thing that you'll want to consider is how much space you'll need to fit through the door, plus a few extra inches to give yourself a little room. And we'll call that space D0 or D naught. And next we'll want to know what angle that corresponds to. And if we consider the door having length L, then our D naught will be at some theta angle. And we can solve for this theta by using the law of cosines, where both a and b are equal to L, the length of the door, and c is d naught. And then we can manipulate that equation to solve for theta, and we'll call it theta rec or theta required. The next question is, how do we actually measure it? And we decided to measure in terms of work. General physics tells us work is the integral of f dot dl, and in this case, dl is in the theta direction, where that's essentially just an arc length. So we have an L, which is our length of the door, times d theta, which is the change in the angle. So if we start at some angle theta I and go to our theta rec, then we can solve the f dot L times d theta, but f dot L is essentially just the torque, and so our work ends up being just some torque times the difference in the required minus the initial angles. Next we want to find out what this torque is, and initially the door is swinging towards you at some initial angular velocity, and at the end it's going to be moving at some final angular velocity, but you want it to be moving at a tangential velocity that's equal to your own, so that it moves with you as you go through the door and doesn't change yours, which means that the angular velocity, the final one, needs to be something like this. And with that, we can go ahead and start writing the angular momenta, which is just the moment of inertia times the angular velocity. And the moment of inertia here, if we have some uniform mass density, then it'll look something like this for a door. But for now, we're going to take a look at the change in angular momentum, because we're going to later use that for the momentum impulse theorem for angular components. So the change in your angular momentum is equal to some torque times the time that torque is applied. And we're going to assume that the time is pretty small, so that the torque is essentially this thing here. And then we can go ahead and plug that torque back in to our work, and we get something that looks like this. Moving forward, we'll mostly be trying to solve for different initial angular velocities, but first we're going to look at the work of a closed door, so where the angular velocity, or the initial angular velocity, and the initial angle are both 0, and that will be this thing here. And if this thing is less than the other work of the other door, then you should take the closed door, but otherwise you take the open door. Note here that both of these are in units of work, and that theta naught, if theta naught is greater than the required angle, then the work is negative. So that essentially means that doing any additional work wouldn't help you get through the door. Next, we're going to look at automatic door closers. First thing we're going to consider is something that looks like a spring, which will have some torsion coefficient, very similar to something like a mousetrap. And here, there's going to be some torsion, or torque, which is equal to the torsion coefficient times the angle, similar to how a mass on a spring would be with the displacement times the spring constant. And that's going to be equal to some force times the moment arm. And we can just solve for the force, And now we have almost what we need for Newton, but first we're going to want to try and map what the actual door is doing. And so it's going to have some angular acceleration, which is going to be the second derivative with respect to time of the change in theta, and that times the moment arm. Next, we're going to go ahead and set up Newton's equations. So the F is equal to ma. And we'll substitute in what we had done previously. And then we'll try and manipulate it so it looks like a differential equation that we can solve, which is this thing here. And this should have a general solution that looks like this. It'll be a cosine function. We'll represent these constant terms by just one big constant term, c. And this change or this angular velocity, essentially, is what we're looking for. So we'll first deal with these coefficients, a and phi, which can be represented by initial conditions of the theta at time 0 and the change in theta with respect to time at time 0. And those look like this. But what we're really concerned with is what omega naught is, which is going to be very closely related to this change in angular velocity. And so if we look at our diagram again, we know that the time that we're going to be very concerned with, or the time at omega naught, is going to be essentially as soon as you grab the door, or as soon as the door hits your hand. And we're going to represent that by something called t0. And for the rest of the presentation, we'll be calling it t0. And so now to solve for the work, we essentially just plug t0 into our theta dot equation, and then plug that back into the work equation. This sort of mousetrap idea is essentially an undamped case, but we're probably not used to seeing an undamped case because those doors would close very quickly. I mean, it would be very, very similar to a mousetrap. What we're usually used to is something that looks like this, where it has an automatic closer that is damped. And we have a quick experiment to show you what that looks like. All right, for this experiment, we just have a piece of paper with a couple different angles written on it. And the idea is that we'll put this piece of paper underneath the automatic closing door and measure at different angles the time just on a stopwatch. And from that we'll be able to determine the angular velocity and the angular acceleration. And we'll do that a bunch of times and then plot the data and see what it looks like. So because Newton needs both acceleration and force, we got this door pressure gauge, which measures in pounds the force on the door. And if we push just right about here, about where you'd put your hand, then we can see that it's about 2 pounds as we push open the door. There's a little resistance there. But then when we're coming back, as the automatic door closer sort of starts to dampen, so it goes down sort of to 1 pound. We were able to make 3 plots from the data. This first one shows the angle versus time. And you can see the first couple points go down very drastically, and the rest sort of, they look like they're damped, like it's slowly going to 0. And you can see that on this velocity versus time, that initially it's very fast, and then it slows down. And then right at the end you see a little bump, and that's because sort of the door had almost a release function right at the end, and you can see that also on this acceleration versus time. We're next going to look at the math for some of the damped cases. The main difference being that now instead of just having the force equal to some f of theta, it's also some additional force. And that additional force is going to be something to counteract that angular velocity. So it's going to be some constant times the moment arm times the angular, the change in angular. with respect to time. And then we can set up the differential equation. Here, instead of just representing c by a constant, we also have this other constant. And we choose these because it kind of makes the solutions easier. So we'll have 2 beta and also c squared. We'll have 3 cases, one for each of the possible relations between beta and c squared, or beta squared and c squared. The first one is going to be an underdamped case, the second is critically, and the last one is overdamped. We won't consider the underdamped case because we want it to look something like our experiment, so we'll look at overdamped and critically. Looking back at our differential equation, we know for the critically damped case that beta is going to be equal to c squared, or beta squared is equal to c squared. And so what we have is essentially these solutions to the equation, and then our omega naught, which at t0 is the derivative of that those solutions, looks like this, and it would suffice to essentially plug this back in to our work function up at the top to get a solution for a damped door closer, for the work at least. These coefficients, a and b, are essentially these things here. And that should be most of what you'll need for a damped door closer. And last, we'll look at the overdamped case. Here, it's also going to be a decaying exponential, similar to the critically damped, but beta squared is going to be greater than c squared. So there's also going to be a positive exponential term with respect to t. And that's this one here, the a1 term. So it'll decay a little slower than the critically damped case. But when we solve for omega naught, the derivative here is going to be a little more complex than the derivative for the critically damped case. But essentially it looks something like this. And notice here a1 and a2 are different than the a and b from the critically damped case. And you can solve for those as well here, in case you have those initial conditions and you want to test it. I think it's also important to note that the first couple points that we saw on those graphs, they sort of resembled an undamped case, and that was true with the door as well. That it sort of had an undamped phase, and then it hit a certain dampening, and then right at the end it went back to undamped. But the main takeaway from this entire project is that if the work, the W here is the work by the required for you to open the closing door, the open door, and then WCL is the work required to open the closed door to your required angle, and whichever one of those is less, then that's the door you want to take. Thanks for watching, and thanks for USF and Dr. Shi.